Welcome to Astronomy Daily, your regular dose of cosmic insights with your host, Anna. Today, we're diving into how a massive ancient impact shaped our planet for life, uncovering new secrets about ice and space, and getting the latest on exciting space missions and rocket launches. Plus, we'll guide you through observing July's beautiful buck moon and commemorating a historic lunar anniversary. Let's get started with a story about our home planet. Earth, alone among the rocky planets in our solar system, is a vibrant home for life. It's warm, hospitable, and teeming with activity, a stark contrast to the frigid lifelessness of its neighbors. How did our planet become so uniquely suited for life? The answer is incredibly complex, but a significant part of it lies in the fascinating field of cosmochemistry, which explores how chemical elements are distributed across the cosmos. Imagine our solar system 4.5 billion years ago. It was a far more chaotic place than it is today, with planets still in their infancy, and countless planetesimals and planetary embryos whizzing around, constantly crashing into each other. Amidst this cosmic demolition derby, something extraordinary happened. Earth somehow received an exceptionally generous delivery of carbonaceous chondrites. These aren't just any space rocks. They're packed with amino acids and other essential chemicals, the very building blocks that enable life. Cosmochemistry studies have revealed that between 5 and 10% of Earth's entire mass originated from these carbonaceous chondrites that collided with our young planet. What's even more astounding is that a substantial portion of this life-enabling material is believed to have arrived during the colossal impact event that formed our moon, the Theia impact. To rigorously test this profound idea, a team of researchers, led by Duarte Branco from the Institute of Astrophysics and Space Sciences in Portugal, utilized sophisticated dynamical simulations of the solar system's formation. Their groundbreaking work, titled Dynamical Origin of Theia, the Last Giant Impactor on Earth, is set to be published in the journal Icarus. In cosmochemistry, a critical distinction is made between carbonaceous chondrites, or CCs, and non-carbonaceous meteorites, NCs. This effectively divides the solar system's meteorite population into two distinct material reservoirs. CCs formed much farther from the Sun, likely beyond Jupiter, and are rich in volatiles like water and organic compounds. NCs, on the other hand, include things like iron meteorites and contain far fewer volatile elements. The core question for the researchers was whether Theia could have delivered these crucial CCs and volatiles to early Earth. To investigate this, the team ran detailed N-body simulations focusing on the later stages of terrestrial planet growth, specifically after the solar system's gaseous disk had dissipated. These simulations included CCs that were scattered inward as gas giants like Jupiter and Saturn were still growing. The researchers explored three main scenarios, one with only small CC objects, or planetesimals, another with only large CC objects, or planetary embryos, and a mixed scenario that included both. A subset of these simulations also factored in the giant planet dynamical instability, better known as the NICE model in astronomy. This model describes how the giant planets shifted their orbits from their initial formation positions. The goal was multifaceted: to understand how CCs and NCs were distributed, why Earth ended up with significantly more CCs than other rocky planets, particularly Mars, and whether the Theia impact was indeed responsible for delivering a large amount of Earth's CC material. One of the most striking results showed that the giant planet instability, especially Jupiter's orbital shift, had a profound effect on Earth's accretion of CC material. As the giant planets moved, they caused a strong pulse of eccentricity excitement, leading to a wave of collisions and ejections, effectively flinging CC-rich material into the inner solar system. Crucially, the simulations strongly supported the idea that Theia itself was a carbonaceous object. In the mixed scenario, simulations without giant planet instability, Earth's final impactor, Theia, included a carbonaceous component in more than half of all simulations. In 38.5% of cases, Theia was a pure carbonaceous embryo, and in another 13.5%, it was an NC embryo that had previously accreted a CC embryo. This paints a vivid picture of the early solar system: two distinct rings of planetesimals, an inner ring of rocky material, and an outer ring of carbonaceous chondrites. As the ice giants migrated inward, They propelled this CC material into the inner solar system, with more massive ones preferentially scattered into the orbits of the rocky planets. This explains not only the masses and orbits of the terrestrial planets and the distribution of asteroids, but also why Earth has a higher CC mass fraction compared to Mars. It suggests that Earth's final giant impact was indeed with Theia, and that this object had a higher concentration of carbonaceous material, directly contributing to our planet's habitability. The simulations indicate this last impact occurred between 5 and 150 million years after the gas disk dispersed, with a large fraction happening within 20 to 70 million years, timings consistent with current understanding of the Theia impact. Moreover, the research emphasizes Jupiter's pivotal role in shaping the solar system's architecture, not just by truncating the asteroid belt, but also by scattering crucial carbonaceous material from the outer solar system into the path of the rocky planets, especially Earth. Ultimately, the formation of a life-sustaining world like Earth required an astonishing number of variables to align perfectly. This research highlights that it may take more than simply being in a habitable zone for an exoplanet to support life. The complex dance of outer giant planets migrating and delivering carbon to inner rocky worlds might be another critical, often overlooked ingredient in the recipe for life in the universe. All right, moving on. Prepare to have your perceptions of space ice completely shattered. For decades, scientists have largely viewed water frozen in the depths of space as a shapeless, amorphous fog, too cold and still to ever form orderly crystals. It was believed to simply freeze straight from vapor onto cold surfaces like dust grains in comets or icy moons, without any structured shape whatsoever. But a groundbreaking new study by researchers from University College London and the University of Cambridge is challenging that long-held belief. By combining incredibly detailed computer simulations with carefully controlled lab experiments, this team has discovered that space ice is not entirely amorphous after all. Instead, it holds tiny, hidden crystal structures within its disordered form. These small, organized patterns could fundamentally shift what we know about ice, water, and even the very origins of life in the universe. On Earth, ice typically forms a neat, crystalline pattern, visible in the intricate symmetry of a snowflake. But in the extreme cold and vacuum of interstellar space, where temperatures plummet far below freezing, it was thought that ice formed without any order. This form of water was known as low-density amorphous ice, and the prevailing view was that it lacked any internal structure. However, that view is now rapidly changing. The researchers began by freezing virtual boxes of water molecules down to an incredibly chilly -120 degrees Celsius. This allowed them to simulate how ice forms at various rates. Some simulations indeed produced nearly perfect disordered ice. But others revealed something fascinating. Tiny crystals, roughly 3 nanometers wide, that's just slightly larger than a strand of DNA, began to form within the chaos. The result that most accurately matched existing X-ray diffraction data wasn't fully disordered ice. Instead, it was found to be approximately 20% crystalline and 80% amorphous. Dr. Michael B. Davies, the lead author of this pivotal study, noted, "We now have a good idea of what the most common form of ice in the universe looks like at an atomic level." He emphasized the importance of this finding, explaining that ice is involved in many cosmological processes, for instance, in how planets form, how galaxies evolve, and how matter moves around the universe. The team didn't stop at simulations. They meticulously created real samples of amorphous ice in their lab using several methods. One method directly mimicked how ice forms in space, by depositing water vapor onto a surface chilled far below freezing. Another involved crushing normal ice at very low temperatures to produce high-density amorphous ice. After creating both types, the researchers carefully warmed the samples, allowing crystals to develop. Here's where it got even more interesting. They observed that each sample produced a different crystal pattern once it warmed. This was a critical observation. If the ice had truly been fully amorphous, completely without any order, it shouldn't have retained any memory of its earlier form. But because it did, the scientists concluded that even space ice, despite its seemingly shapeless appearance, retains some hidden structure within. As Professor Christoph Salzmann, a co-author of the study, put it, "Ice can remember its previous structure. The order of hydrogen atoms in a crystalline state can be preserved even as conditions change." This suggests that space ice is far more complex than previously thought, carrying clues about its origin and the environment in which it formed. These findings have significant implications, particularly for theories regarding the origin of life beyond Earth. One prominent theory, known as panspermia, suggests that life's essential ingredients, such as amino acids, may have arrived on Earth from space, perhaps carried by comets. This idea relies on space ice being able to effectively trap and protect complex molecules during their long journeys across the cosmos. However, this new discovery complicates that idea slightly. As Dr. Davies explained, our findings suggest this ice would be a less good transport material for these origin-of-life molecules. That is because a partly crystalline structure has less space in which these ingredients could become embedded. While this might weaken the panspermia argument slightly, it doesn't rule it out entirely. Davies added that the theory could still hold true, as there are amorphous regions in the ice where life's building blocks could be trapped and stored. Ultimately, these results provide a more realistic picture of the conditions life's precursors might encounter while traveling through the vast emptiness of space. The implications of this research extend far beyond just the origin of life. Amorphous materials are incredibly common in modern technology. For example, the glass used in fiber optic cables, which transmit data across the globe, must remain in a disordered state for optimal performance. If these materials contain tiny, hidden crystals that could affect their performance, understanding how to remove them could lead to significant advancements and better technology. Professor Saltzman also highlighted this, stating, "Our results also raise questions about amorphous materials in general. These materials have important uses in much advanced technology. If they do contain tiny crystals and we can remove them, this will improve their performance. Furthermore, this knowledge could help space agencies design more effective spacecraft. Ice in space isn't just a passive substance. It has the potential to serve as radiation shielding or even as a source of fuel if broken down into hydrogen and oxygen. Knowing more about its various forms and structural properties could lead to smarter and more efficient uses for this vital cosmic resource." As Dr. Davies noted, ice is potentially a high-performance material in space. It could shield spacecraft from radiation or provide fuel in the form of hydrogen and oxygen. So we need to know about its various forms and properties. Next up today, let's take a look at launch plans. As you well know, we're constantly looking to the future in space, and some truly ambitious plans are on the horizon. Chinese scientists have put forward a fascinating proposal for the country's very first ice giant mission. Their goal is to launch a radioisotope-powered spacecraft by 2033, destined to orbit Neptune and conduct an in-depth study of its mysterious moon, Triton. This mission promises to shed new light on one of the most distant and least understood worlds in our solar system. Closer to home, it's been a bustling period for rocket launches, even in what was described as a quiet week for orbital flights. SpaceX recently achieved a monumental milestone, completing the 500th orbital flight of its workhorse Falcon 9 rocket. This incredible feat was part of their Starlink Group 1028 mission, which lifted off from Cape Canaveral Space Force Station. The Falcon 9 has certainly earned its reputation, celebrating over 15 years since its inaugural flight in June 2010. This 500th launch saw booster B-1077 make its 22nd flight, a testament to the reusability pioneered by SpaceX, with the booster aiming for its 490th recovery attempt on the drone ship, a shortfall of gravitas. In late June, SpaceX also set new records with back-to-back launches from Florida and California, marking their 80th and 81st Falcon missions of the year. They even achieved a new pad turnaround record of just over 56 hours at Space Launch Complex 40. This relentless pace has contributed to a significant increase in global launch cadence, with 142 orbital launches worldwide in the first half of the year, a 16% jump compared to 2024. Keep an eye out, as another Falcon 9 launch is anticipated soon, possibly carrying the Israeli Dror 1 communications satellite into geostationary transfer orbit. Meanwhile, on the other side of the world, Australia is gearing up for a historic moment in its space program. Gilmour Space is preparing for the highly anticipated maiden launch of its Eris small satellite rocket. This will be their second attempt after the previous one in May was postponed due to a power surge that prematurely triggered the fairing separation system, an issue that has since been successfully mitigated. The Eris rocket is set to lift off from the Bowen Orbital Spaceport at Abbott Point, making it the first orbital launch from Australian soil performed by a sovereign-built vehicle. Standing at 25 meters tall and boasting a payload capacity of up to 215 kilograms to a 500-kilometer sun-synchronous orbit, Eris is comparable in size and capability to Rocket Lab's Electron. Its first stage is propelled by 4 proprietary Sirius hybrid engines, which use a unique 3D-printed solid fuel grain and hydrogen peroxide as the oxidizer. A successful orbital launch would also mark a significant first for a hybrid rocket design, showcasing a new frontier in propulsion technology. Now let's turn our gaze to the night sky, because July 2025 promises a spectacular lunar event. The full moon, affectionately known as the buck moon, is set to rise on Wednesday, July 10th. This celestial display is perfect for both seasoned stargazers and budding astrophotographers. A full moon occurs when our moon is perfectly positioned opposite the sun in the sky, allowing it to appear completely illuminated from our perspective here on Earth. The buck moon gets its evocative name from the time of year in North America when male deer, or bucks, are actively growing out their impressive antlers. It's also sometimes referred to as the thunder moon, a nod to the frequent summer storms that rumble across parts of the U.S. in July. This year, the buck moon holds another distinction. It arrives less than a week after Earth reaches aphelion, its farthest point from the sun in its orbit, making it the most distant full moon from the sun in 2025. While the moon technically reaches its fullest phase at 4:36 p.m. Eastern Daylight Time, or 2036 GMT on July 10th, it won't be visible to us until it rises above the southern horizon at sunset in your local time zone. For instance, if you're in New York City, you can expect moonrise around 8:53 p.m. local time. Remember that exact timings for moon phases can vary depending on your location, so it's always a good idea to check a trusted website like inthesky.org or timeanddate.com for precise local timings. You might notice something particularly striking about July's full moon. It will appear exceptionally low in the sky after sunset. This phenomenon is largely due to its proximity to the summer solstice, the time when the sun is at its highest point in the daytime sky. Consequently, the moon tracks a correspondingly low path through the night. This effect is even more pronounced in 2025 thanks to a fascinating occurrence known as a major lunar standstill. This happens approximately every 18.6 years, when the sun's gravity influences the moon's tilted orbit, pushing it to its most extreme inclination relative to Earth's celestial equator. This orbital dance causes the moon to appear either exceptionally high or, as in this case, notably low in our sky, depending on the time of year. As you observe the buck moon, especially in the hours following moonrise on July 10th, you might experience a common optical illusion, the moon illusion. This is when the lunar disk appears larger than it actually is when it's positioned close to the horizon. Our brains, for reasons still debated by scientists, trick us into thinking it's bigger than it appears when directly overhead, even though its actual size in the night sky remains constant. You might also notice the buck moon take on a beautiful golden or reddish hue shortly after it rises. This warm coloration is caused by Rayleigh scattering, the very same atmospheric effect that paints our sunsets and sunrises with vibrant colors. When the moonlight reflected off the moon's surface travels through more of Earth's atmosphere to reach us at the horizon, the shorter, bluer wavelengths of light are scattered away, allowing the longer, redder wavelengths to pass through more directly. Beyond the enchanting display of the buck moon, this month also marks a significant anniversary in human spaceflight history, the 56th anniversary of the Apollo 11 moon landing. On July 20th, 1969, Neil Armstrong and Buzz Aldrin became the first humans to walk on the moon, while Michael Collins expertly orbited above. To commemorate this incredible achievement, we invite you to try and locate the 6 historic Apollo-era landing sites on the lunar surface. With the naked eye, you can often spot the general region visited by each Apollo mission. But if you have access to a 6-inch telescope, it will greatly enhance your viewing experience, helping to reveal finer details in the rugged moonscapes and smooth lunar seas surrounding each of these historic zones. It's a wonderful way to connect with a pivotal moment in our shared human journey of exploration. That's all for this episode of Astronomy Daily. We hope you enjoyed our journey through cosmic origins, the secrets of space ice, and the latest in space exploration and sky watching. A quick reminder before I log off. Visit astronomydaily.io to sign up for our free daily newsletter and explore all our back episodes. Remember to subscribe to Astronomy Daily on Apple Podcasts, Spotify, YouTube, or wherever you get your podcasts. Until tomorrow, this is Anna reminding you to keep looking up and marveling at our wonderful universe.